in order to create circuits where every single value correlates to a different redstone impact. So if we go into our library of Minecraft modules, and just sneak in here, we go to our counter. Do you guys remember me showing you this contraption here? Albert, do you remember this? All right, so we might not have gone to it. That's okay. What this contraption does, we're actually going to, is each one of these is just a T flip-flop. If I hit this, the light goes off. If I hit this again, it goes on. This is just another version of the T flip-flop design. However, it's done in such a way that we can connect another T flip-flop to it really conveniently. We put a block in the redstone repeater, and then we have another T flip-flop. So I'm going to break this one for now. So it's just these two. Now let's say I hit this button. Let's go back to 0, 0. Right. I mean for lovers. So right now, ignore these lamps. I'll actually break them for now. We'll put them back later. We have these two lights that are off. If I hit this once, the first one's going to turn on like a regular T flip-flop. If I hit this a second time, this one's going to turn off and this one's going to turn on. And if I hit it the third time, now they're both on. And if I hit the fourth time, we're back to 0. And what each of these represents is, this represents a machine that can count. This redstone lamp can either hold the value 0 or 1. And then this redstone lamp can go up to 2. So if we get up to this redstone lamp, this can hold a maximum value of 2. And then if we keep going, it'd be 4 and then 8. So if the fourth redstone lamp, if we grab a redstone lamp and put it back, was the only one that was on, then the counter would have a value of 4. And if the third redstone lamp and the fourth redstone lamp were on, it'd be 4 plus 8. But this system of counting is a little bit more complicated. So what we're going to do is we're going to go over the base 2 system, which is what this system of counters is based on, counting in binary. And how counting in binary is how computers count. Computers only understand things in ones and zeros. So to a computer, this first redstone lamp is either a 1 or a 0. It's either on or off. The second redstone lamp is either a 1 or a 0. It's either on or off. This is either 1 or 0, on or off. And so this current combination would be 1000 because this one's on, 100, this one's on, 0, 0. So 1100. So what we're going to do now is we're going to pass off to John. John's going to explain the counting system in a little bit more detail, and we're going to put some things in our lab book to remember this, because this is really important for both redstone and counting in general. So
great.
John, go ahead.
Okay, let me share my screen. Okay, so as Thomas said, our human brain, we tend to think in the decimal system, 10 digits. Maybe that's because we have 10 fingers. I'm not really sure, but some people speculate that. But as Thomas said, computers really think just of 2 numbers, 0 and 1. And the advantage that computers have over humans is that they can distinguish between a 0 and 1 very, very, very fast. They don't have all the nuances and complexities of our human brain, but they can go lickety split. So hence a new number system evolved called Boolean, the Boolean number system, to accommodate the fact that computers like to think just in terms of 1s and 0s, not in terms of 0 through 9. And here's the truth table that Thomas was just talking about. As you can see in the decimal column, we can have 4 states. We start with 0 is the first state, and then 1, 2, 3. And Thomas just showed the physical representation of this. So
And
there's
guys, let's make
four.
sure we put this table into our lab books to help us remember it. This is really important. And the quicker we understand this, the easier we'll be able to build in Redstone.
Right. Ultimately, you're going to need this table in order to decode, so that if you want to do a rainbow-like fireworks, as Thomas was showing you, on the count of 0, we're going to decode all the counters so that when we see a 0 and a 0 and a 0, then we'll turn the first firework rocket on. And then on the next cycle of the oscillator, we'll see a 0 and we'll see a 1 and a 0 and a 0. And that will trigger the second color in our rainbow. And then on the third cycle of the oscillator, the counter will go to the third state, or the count 0, 1, 2. And we're going to decode these outputs in an AND gate, using inverters and an AND gate. So we'll give you 3 minutes to document this table in your lab book, in your PowerPoint lab book. And we're going to need this table in order to design our decoders. So Thomas, the way I would think of this, there might be quicker ways to do this in Minecraft, but the way I would think about this if we're designing an electronic circuit is that you could just put the outputs of the counter when they're all 0. The first decoder is invert all the outputs, and then put the inverted outputs of all the counters into an AND gate, and that will detect the 0. And then for the second state, you just put an inverter on the second stage of the counter, and then the direct output of the first T flip-flop goes into the AND gate, and the inverted output of the second T flip-flop goes in the output. Is that the way you would design it, Thomas?
So what I'm going to do is right now we have a couple lights on here. We went over quickly how to count in Boolean. So let's see if you guys can figure out what number this represents. I'm going to hit it a few times. Get a different number a little bit. And let's, I'm also accidentally launching some fireworks. It's okay, I'll launch a bunch of them if you guys get this right. Oh, I disconnected the redstone. That's awkward. All right, let's hit this. Let's make it a little bit more complex. All right, I'll hit like 5 more times. All right. All right, here we go. Let's start with this one. I'm going to TPS all out here, just so you guys know.
Is it 5?
All right. We have one person saying 5. All right. Any other guesses? And let's see. Can someone tell me what it is in base 2? So using just 1s and 0s. What number is this? This is whoever said 5 was right. That was spot on. This is the easier one. What number is this in base 2? In binary. Any guesses?
10100.
Yeah. So this is a 101. So just 101, John. It's from left to right.
Yeah.
So these two So if we think of this in binary, remember, this is the first digit of our number. Our number can go all the way up to 11,111 if they're all on. If this one's on, this represents a value of 16 or 10,000. If this one's on, it represents a value of 8 or 1,000. If this one's on, it represents a value of 4 in base 10 and 100 in base 2 binary. This one represents either 10 or 2 or 2, 10 being binary. And this one represents either 1 or 0 in both base 1 and base 10. So if we're trying to read a number in base 2 from Redstone, we start at the right, the farthest oscillator, and we look at this. Is it on or off? It's off. So the first digit, the 10,000 digit, is 0. So this number at most can be 1,000. We look at the 1,000 digit, the fourth digit in our number, it's also 0. So this number can't be more than 100. The 100 light is on, so it's 100 something. The 10 light is off, so it's 100 with nothing in the 10's place. And then the 1's place is on, so it's 101. If I cheat a little bit because I don't feel like clicking everywhere, and I put a redstone lamp, it's fine actually. If this light were on, I will. That's annoying. If this light were on, it would be 10,101. All right. So what we're going to do now is I'm going to explain how this works, and we're going to try and build at least one of these for now. And then if you get one, start building the second to start off. We'll start off just 2 because it's easier to understand the lower numbers. So this works, the left part of this, if we recognize this, is just the exact same as the T flip-flops we've already been over in class. This is if we build our T flip-flop quickly, and then we build it out, and we have the block here. We'll put the repeater on our redstone block. There we go. This right part of it is the exact same here. It's just the right part of the T flip-flop. What it does is it sends only a partial signal through to here. So this dust, when we hit the button, is going to turn on for a second and then turn off immediately afterwards. Then we go into the crux of this T flip-flop. Instead of using a redstone block, which we could use but is slightly less convenient, doesn't fit as well, isn't as linear, we're going to use a little bit of a sand contraption. So the first time you send a signal here, it gets this repeater. This piston's going to get activated no matter what. So every time I hit this button, the piston's going to get activated because of the repeater signal to this piston. However, when the lime block is up, the lime block of wool is up, the signal stops here. It can't get to the rest of the T flip-flops because there's no block here. However, then this repeater is going to get powered, which means the next T flip-flop in the line is going to essentially do the same process as our first T flip-flop, only it can only happen when this block is down, and this block is down every other time. So this is why the block that represents 2 here, you have to hit this. This light needs to change twice before this can change. So I hit it once, it changes. I have to hit again. It's not going to change this time. Hit the second time, it's going to change again. And this one, you need to hit the button 4 times to make a change on this block, 8 times to make a change on this block, 16 times to make a change on this block, and so on and so forth. And the top design is just part of our T flip-flop. We have a redstone torch connected to a repeater. And when the block of wool is up, the sand block gets pushed up, and the signal is going to pass through. It's going to get to this redstone dust, which is going to depower this torch. So it's going to be off. We hit the button. Now the block of sand falls. This signal cannot get to the redstone dust. As a result, this redstone torch is going to be active, and it's going to power the lamp. Does that make sense to everyone?